Okay, so let's talk about the upcoming schedule a little bit and what we're going to be doing for the rest of the week, because there's quite a bit that is going on in the class, right? We have our big project that we're working on that's due on Friday. And in the meantime, I've been introducing some new design patterns as we go. So this week, I'm anticipating there being 2 to 3 work days throughout the week where people can work with others, get some feedback on how your project is going. I think that would be especially useful considering this is probably the most involved thing you've written to date. And this is going to be a process, and I want to make sure that that process goes as smoothly as possible. When we're not having work days, I'm going to be introducing some new design patterns. We're probably going through about 3 more this week. They're all reasonably short. They're not as involved as factory and abstract factory, at least to introduce to people. So that won't be quite as bad. We'll be able to get through them in a couple class periods. Starting next week, there's going to be an additional small lab on the factory pattern. And then I'm also going to introduce the next project. There will be two bigger projects, the one you're working on right now, and then the next one starting next week that will take the last 2 weeks of the course. That will use some of the design patterns that we've been covering, like factory, and then the next 2 or 3 that we're going to go over this week. Then finally, I will kind of blitz through the remaining design patterns in the last couple of weeks, and there will be one more small lab on one design pattern that is very important, but won't be part of either of the major projects. That'll be the observer one. So that's kind of where we are. There are going to be 2 more small labs, 1 more large lab, and those will all come after this week, after your project is in. So that's where we are. We're going to cover the remaining design patterns today, starting today. So the first is the bridge design pattern. So as you might anticipate, bridges together something. And I apologize in advance, these are all just going to information dump because the animations were lost when my computer blue screened. Oops. So one thing to think about is when we're producing something, our abstraction and our implementation are in the same hierarchy. What that means is we have an interface and then some classes that implement that interface. And maybe the first thing that gets implemented from that is an abstract class. And the abstract class implements the interface. And then we have some concrete classes that extend from that abstract class. As we do that process, there are some concerns that might show up. So what Bridge is going to do is it's going to separate the abstraction from the implementation and create 2 separate inheritance hierarchies, one for the abstraction, one for the implementation, and then the implementation will be composed of the abstraction. So we will split the abstraction from the implementation. If we have an arbitrary number of abstractions and an arbitrary number of implementations, then we end up with disgusting numbers of subclasses that are coupled together in ways that are not extendable. So as usual, this is a way to abstract something and make it further extendable. So we will have both of these being separate inheritance hierarchies that are bridged together by the bridge pattern. The simple way to think about this is we have the abstraction that is the shape and the concrete that is the color. So if we do this together, we end up with a shape and a color as a subclass from an abstract class that we will call shape. So just looking at the bottom right of the slide here, we see that we have 4 subclasses for different kinds of shapes. We're combining together the abstraction and the implementation together, so we end up with a red circle that has the defining characteristics of it is red and it is a circle. Same with red square, it is red and it is a square. So we learn now that we want to extend this functionality to be able to add additional color to our shapes or additional shapes to our shapes. So we start small and then we try to add a triangle shape. How many classes do we need to create? 2 classes, because the triangle can either be red or blue. We add a green color. What changes do we need to make? We need a green circle, a green square, and a green triangle. What happens if we add a pentagon? Yeah, exactly. We have a number of classes equal to, if this is a concrete, if this is our implementation, if this is our color, then we need to add the number of shapes. If we add a new shape, we need to add a number of subclasses equal to the number of colors that we have. And that grows geometrically, 1 plus 2 plus 3 plus 4 plus 5, that's a geometric progression. So it grows geometrically as we add more and more functionality to this. And that's kind of gross. So we can simplify this by having kind of moving this into 2 separate inheritance hierarchies, one for shape, one for color. The shape is going to contain a color. So if we make a square object, it'll have a field for its color rather than being defined by part of the class. So splitting the hierarchy by the dimension like this makes a lot of sense, especially when you have something where it's obvious that it should be composition. But a lot of the times when you see bridge being used, it's not obvious that this composition could exist. We choose a really simple example like shapes and colors because it makes sense. It's easier to grasp than a more complicated example. But if you were to see something that was a real world example like this, you might not think, oh, this large inheritance hierarchy could just become a composition of 2 separate components, and then you're fine. If you use this hierarchy, what happens if you want to add a new shape? One thing, we need to make the new shape class, and since the shape class can contain any of the associated colors, if we made a triangle class here, then we could make a red triangle or a blue triangle without adding additional subclasses for the red triangle or the blue triangle. We just have a triangle class that can take on all of the existing colors. What happens if we added a green color? How many changes do we need to make? Single change. And we can now make a circle or a square or a triangle that is red or blue or green with only a single class change. So we've gone from a geometric progression to not only a linear progression, but a constant progression where it's always one new class. No matter how big the shape hierarchy is or how big the color hierarchy gets, it's a single change. So it doesn't change with the number of shapes or colors that are in the implementation. Straight up doesn't change. Let's take a look at a slightly more realistic example. We have an application with multiple components. One of these components is a graphical user interface. We call that a GUI. This by itself is just the menu layout, what the screen looks like, what the user is actually interacting with. And then we also have the backend that describes how are we communicating with the operating system, how are we communicating with storing data and retrieving data. But doesn't it make sense that we might want to swap out the back end and keep the front end, keeping the GUI looking the same? What is the difference between this program interacting with a Windows operating system and a Mac operating system? There are differences, but it doesn't really change how we want the graphical user interface to change. So we could have a separate hierarchy for displaying the user interface and another separate hierarchy for the associated operating systems that we support. So we could create a bridge between that, and that way we could add support for a separate operating system without changing the GUI at all. We could make changes to the GUI and those will propagate to all of the classes that we have written for support for different operating systems. We've now decoupled the graphical user interface from the code that makes it work with the associated operating system. And that is a huge amount of time and effort that is saved when we want to do this, because every feature that you would implement, you have to think about how is this feature going to be parsed or used in different operating systems. And we don't want that level of complexity in our code when we go to extend it. All of that work should already be done in some other hierarchy that we can just compose. It's especially relevant if we have different GUIs that want to be on different operating systems. If you're working with a Windows desktop, you'll want one GUI. If you're working with an iPhone, you'll want a separate graphical user interface, right? Because interacting with a phone is different from interacting on a desktop. The way you're going to want to display things are very different when you have more screen space, when it's more horizontal than vertical, or more vertical than horizontal. Those things all change. So it's especially important that we handle all of this and make it extendable, especially if we want to do something like support a new operating system. You don't want that to change and break the existing code. Questions on this example? We'll look at another example. We're going to design a series of remotes. Each remote operates a different model of television. We have an abstract interface, abstract class, something abstract for the remote. And then we want to be able to design different remotes for different TVs with slightly different features. So one thing to note, it's only the first design of the remote. So we want the ability to change things up or extend it in the future. And if we have something like this set up, we have an abstract remote control. We can turn the TV on, we can turn the TV off, we can set the channel, we can do some other things that we might want to do to a TV. Then we have some implementations, each for different kinds of TV. You can tell how dated the book is. So we have implementations for how to communicate with different TV models. How extendable is this? How easy is it to add a new TV model? It's actually quite easy. Adding a new TV is just fine. We just have to define what the communications are, what the on and off and set channel does for that new TV. Great, it works. What happens if we make a change to the remote? Add a new functionality to the remote. In modern TVs, there's now like a Netflix button that launches your smart TV's Netflix app. So let's say we've gone from the day of the book when there was no smart TVs to now oh no, our remotes now need to include a Netflix button. How many associated changes do we need to make?
I have to change all of the subclasses.
All of the subclasses now need to know how we're going to do that. So it's extendable in terms of TVs, but it's not extendable in terms of the remote. So that's what is meant by, well, the TV is open for extension, the remote is not. What could we do about it? What would a solution to this look like?
So the TV has a remote, so have a TV host a remote class.
Interesting. Think about, is it better to have a TV that has a remote or a remote that has a TV? What direction of the composition do we want to go there? You might have multiple different remotes that control the same TV, whereas a TV might have multiple remotes that control it, but each remote only controls a single TV. You don't have a remote that can turn this TV on and that TV on. That'd be really scary if we had a remote to turn all TVs on.
It's not now. I thought that used to be weird.
Yeah, that definitely,
I've been using one forever, so.
yeah,
Then when they were making phones with IR blasters, those out.
yeah. So in,
TV.
to make this as simple as possible, it makes more sense to do the has a relationship between the remote and the TV. So the remote is going to operate a particular TV. And a TV may be controlled by multiple remotes. But the has a relationship is from the remote to the TV to say that this remote controls this TV. And I think that will allow us to be the most extendable and the most realistic. So this has a relationship is what we call the bridge. It's the composition that allows us to have separate hierarchies. So you'll note that we still have the same TV hierarchy that we did before. We still have an abstract class that tells us all of the methods that we need in order to be able to operate a TV. But this also allows us to create different kinds of remotes. Maybe we have a remote for a smart TV and a remote for a non-smart TV that will be able to have the different functionalities for each of those. And you can use a non-smart TV remote on a smart TV. You just have no way to launch the Netflix app with a single button press. Questions about this UML diagram or about how this is an implementation of the bridge pattern? It's pretty straightforward. I think bridge is one of the more straightforward design patterns. The harder part is recognizing when to apply it. So the last thing we should care about are what are some benefits and drawbacks of the pattern. So we will see now that it's very easy to add a new TV. It's also easy to change the remote or add a new remote type. All of that means that it's extendable now in 2 dimensions rather than just for the TVs. So the bridge pattern here does save us a lot, and it is absolutely worth implementing. So some of the benefits we get, the implementation is decoupled from the interface, which is great. The abstraction and implementation can be extended independently. You can just add classes to either side of the bridge, and the communication will stay intact. Also note that if you change the concrete abstraction classes, so in this case, it's like the concrete, that the remote was the more abstract concept here. So if you change the associated class, you swap out one remote for another remote, it doesn't affect the client at all. The client still knows how to operate a particular remote, or it still has the same functionality as it did before, but you can swap it out on the fly without loss of generality, without loss of the client being able to know what they're doing. So you can swap out a TV, you can swap out a remote very easily. So some ideas of when to use the bridge pattern. A graphic or windowing system needs to run on multiple platforms. Makes a lot of sense to switch that out. Vary an implementation and an interface different from each other. So the TV might change, the remote might change, but the has a relationship is always going to be there. So you want to leave room for future modification or extension of either of those components. The drawback, of course, the code complexity increases, meaning that you're going to have more classes. You're going to have 2 separate inheritance hierarchies to keep track of in your code, but you should not need to make changes to either of those hierarchies based on the evolution of your code. It's more complex, but it's more extended. That's basically it for the bridge pattern. Some of these design patterns aren't quite as taxing and intense as the factory pattern. But I think the most important outcome is just knowing when to use it, knowing how to apply it. As always, Refactoring Guru is there to help you with that, but just the exposure to this is important, knowing that this is an option, something that you can do in the appropriate situation. Last minute questions about Bridge? All right, I don't think I want to get into the next design pattern with just a few minutes to go in class. So we can stop a few minutes early if that's okay with everybody. Any remote questions? I don't see anything in chat, but feel free to post anything if there are questions. And we will say that we'll have a work day tomorrow, just so that we can make sure that we are on the right track ahead of Friday. So anyone who would like some additional assistance with coming up with their project, getting started on their project, writing the code, giving their ideas, feel free to come in and get that help. And I will see you all tomorrow.
Thank you.
Thank you.